Hello, and in today's STM32 programming, we are going to be covering reading and writing to the flash memory. Now, we are going to start with the data sheet over here in the embedded flash memory section. So, for this particular STM32, we have multiple SKUs of flash memory. In the case, the chip that I'm working with is a 64 kilobyte flash memory chip. So, in this section, you can see here that there's a table of the flash memory module organization. So this tells us how many pages of flash memory we have. So the first table ranges from page 0 all the way to page 31. So this is a 31 kilobyte flash memory. And then the one we are interested in is we want table 5, which is page 0 all the way to page 127. We can see here the page size in bytes. So you can see every page for the case of this STM32 is 1 kilobyte, which makes our life significantly easier because you can have STMs with different page sizes, especially at the end of the page. So let's look at one of the larger ones. We can see here with the XL density flash module, we have a page size of 0 to 255. Now this is in a single bank. You'll need to specify the bank that you're working with when writing to the flash. All right, now back to the one that we are going to be using, which is the 64K one. So this will range from page 0 all the way to page 63. So we can see that the pages start at hex 8 million hex. So this is the starting address for the flash memory, and this is the ending address for each page. Now here they don't show the 64 page one, but for the 128 kilobyte version, your flash will end at 801 quad F hex. So for writing to the STM32 itself, you need to do a page erase, and then you need to write the entire flash. So you need to read out the entire flash first, check what has changed from what you're writing into it, and then just changing what you need in the flash. So I have a separate sheet specifically for mapping out the pages. So you can see here we start at 8 million hex, and then we increase by 1 kilobyte per page. So if we look at the bottom here, our ending pages is 800FC00 is where our last page starts, and our second last page starts at 800F800. So all of these pages are very simple, increment by 1 kilobyte. You can see it here in the formula, 400 hex plus the offset. Okay, so with that out of the way, we can start with the code. So the first thing we are going to do is we are going to adjust the flash size. So we are going to go into our linker script over here. Unfortunately, this red text is not fantastic for this, but oh well. Then we're going to go to our memory section. This is the default one that you will get when you generate a project. So instead of using the entire flash memory, I'm going to reduce this by 2 kilobytes so that we don't accidentally program into the application code into our storage areas for the flash. So I'm going to reserve 2 pages, and from the datasheet, every page is 1 kilobyte. So I am just going to subtract this by 2. So we have a 62K flash. So if I compile this, you can see here the flash size is 64K. If I compile this, you can see it reduces it down to 62K. So your storage areas are protected. Now you can make separate memory regions for this. I'm not going to do that here because it's not really necessary if you can keep track of this yourself. Okay, now for the code itself. So I've already created a header file and a C file for this. Not anything fancy, just basically a constructor, and that's about it. Okay, so first thing we want to do is we want to create a method to read from the flash, since that is actually the easiest thing to do. So we are going to create a function that is void, and we just call it read, and that's going to take in a uint32_t page start. We're going to use camel case for this. Then we're going to give it a void pointer and say that's the data. And for the length, we are going to pass in another uint32, and I need to copy paste and just say len for length. So this is going to be the starting page address that we're going to write to. This this is going to be the data that we're going to write to the flash, and this is going to be the length of the data that we are going to write to the flash in bytes. Okay, so next is we create again for the C++ file, and we just copy over that, and now we can start implementing. So for page reads, the word size of the MCU is 32 bits, so a single read from the flash memory will always be 32 bits. So if you pass in 8 bits of data into here, you need to match the length of a 32-bit integer. So what we can do is we can create a private function for this, and I'm going to say the name of this function is going to be uint32, and just call the function cal_len. So this calculates the length for us, and that's going to take in the uint32 as the length of our data, and another uint32 for a divisor. Okay, now this is going to be a private function as well, as you can see here, and we copy again over, just set it at the top, give it its name, and we can implement this. And this is a fairly simple procedure. It's going to be a uint32, and we say data_len is equal to len divided by the divisor, and then we say if the data len modulus our divisor, let's give us a brace here, is not equal to 0, then we increment the data len and we return the data len. So this will, if I pass an 8-bit length here, which is 1 byte, and we say the divisor is the size of a uint32, which is 4 bytes, we are going to divide. We are going to find that the data length is 0. We see that the divisor, that the modulus is also not 0, and then we just increment by 1, and that says we have one 32-bit value that we need to read. Okay, then in our read function, we're going to take the uint32, and we are also going to call this data len, and we're going to say equals to cal_len, and our cal_len is going to be our length of the data we want to read, and we're going to say the size of a uint32. All right, then we want to cast our data to a new pointer, so we're going to say uint32 equals flash data, and that is going to be a pointer. We are going to cast it to a uint32 pointer, and that is going to be our data. So we're transforming our void pointer into a uint32 pointer, so that our data lengths match. Okay, then we say for, let's create a index of 0. We say I equals to 0 for our for loop, and I is going to be less than our data len, so the number of uint32s that we are going to read, and we say plus I. Okay, so now we have our loop to read. Now we need to actually read from the flash, so we are going to create another private function. She put that above. We're going to say this is going to be also a uint32, and we're going to say read addr, which is read address, and we are going to tell it we want a uint32, and we are passing it the address location that we are going to be reading. Okay, transfer that over. This actually read needs to be void, so I need to fix that. Okay. Yeah, now we need to actually read the value at a specific address, so that is going to be return, and that's going to be a pointer to _io, actually __io. We're going to say uint32 pointer, and that's going to be a ddr or address. Okay, so let's have a look at this. This is IO. This translates to volatile. So that's all this macro means. It's just a nicer way of saying defines read-write permissions. So it just tells the compiler don't optimize whatever I'm doing over here. So this is going to be a volatile uint32 pointer, and that's going to be, oh yeah, pointer terminology. It's going to dereference it. Oh, no. Yeah, it's going to dereference the address, which will return the value contained in this address, and each address is 32 bits wide. So now we can take our read address, paste that in here. We can say the flash data is I, and now we need to do a bit of math. We're going to say the start page plus I, put that in a brace, plus I times 4. That will give you the 32-bit value. So you move your starting page address by an increment of 4. every time. Okay, and this should be not a magic number. This should be size of uint32. So we start at our starting page, and then every read we move by 4 bytes from our starting page to do a read. Okay, for demonstration purposes, let's just see if this compiles. Okay, successfully compiles. We go look at our main.c. Flash hull is already included. We have a print statement here that I can't remember what it does. Print buffers. Okay, so the useart is not that important for us. So we want to create a Flash API instance. We just say this is flash equals nothing. We don't construct anything here, so it's just that. And then we say flash.read. Let's create something that is a uint8 flash or data, and that's going to be 256. So we're reading 256 bytes. Then we use B0. Believe the STM32 compile, well, the on compiler supports this for the STM32s. The size of flash data, and that shouldn't be referencing it since it's already a pointer. Okay, I'm just going to put in some junk data here. Okay, we need to figure out what the address is that we are reading from. So I'm going to be reading from page 62. So for the starting address, this is the address. So simply just copy that over. And we place that into our code and 0xf. We're going to set a breakpoint here, and we are going to, let's just build that before we try to debug it. Okay, great stuff. We launch the debugger. Have to set up our debugger again because this is a new project. Okay, then on the side you can see here there's a memories tab. You can find this memories tab through Windows, show views, and then you can have your memory and then a memory browser as well. Memory browser. So you can see here from the memory browser, let me just hop back to the flash memory location, F8. You can see here that I've already written in a bunch of ones over here just for testing purposes, but now we can also read out these ones. So let's just run the code to the point where it's B0. Then we can do a step over, and we can see the flash data 0 to 100, all zeros. So that's what the B0 function does. It's just a shorthanded mem set to 0. Then we can step over again, and then you can see here all of this is 17. If we click on it, we can expand it, and then you can see it's hex 11, which matches up with all these values. Okay, so that's effectively a flash read, which is fairly simple. Just quickly stop the debugging process. Flash.cpp. So just to recap, this is the core of the function. All of this is just enabling you to read it into buffers. So very simple. Point it to an address, give it a volatile uint32 pointer that you are dereferencing. I believe this is dereferencing. Comment down below for the correction. Doesn't matter. The fact of the matter is you're pointing to a pointer, and then you're taking the value from that pointer, and your pointer address is the flash memory address. All right, so now the more technical part, doing a flash write. All right, so a flash write is effectively the same. It takes in the same parameters as a read, so we just rename this as write, and we let it return a uint32, which is going to be on our error code. Okay, so we are going to be implementing some where leveling. If you don't know what where leveling is, don't worry, that will become evident as I code this. And we just copy over our function to our C++ file. Okay, and now the first thing we do is we get a hull error, and we're going to say ret, and this is going to be equals to hull underscore okay. Then we're going to take a uint32, call it error. We're going to say that's 0, and we are going to create inj. And then the first piece of processing we do is we do exactly the same as what we do with our reads. We calculate the data length that we are going to write into the flash to the nearest uint32. We again take our void data and cast it as a uint32 type. Now we're going to do the where leveling. So we are going to create a function called validate. So let's say say it's going to be in this function. We're going to say bool validate. I think I spelled that correctly. Let me just double check that. Yes. And that is going to take in the same parameter as a write. Well, actually a write and a read, because technically we are going to read the flash now. Then we're going to create this validate function. All right. And then we declare a boolean inside. And we say should write, and that's going to be automatically equivalent to false. So if we don't need to do a write to the flash, we skip this process. We get a for loop, and we're going to say uint32i. Then we're going to do if our, actually I lie, this needs to be a uint32. So then we don't need to do this cast over and over and over again, because this is a private function. We assume the data is going to be in the correct format. Okay, then we say our data and our index, if it is not equals to our read data, actually exactly how we did it over here. Let's just check if our braces are correct. Looks to be correct. Let's just compile that and make sure, because copy paste error. Just add that to force it to compile. 8 warnings. Let's see what the warnings are. Data len was not declared in the scope. Okay, that's going to be len unused variable warning no return. Okay, doesn't look bad. And then we just say return over here should write. So basically what we're doing here is we are going to skip a flash write if the data is identical that we want to write to the data, because you don't want to wear out your flash. So you have a limited number of times you can write to your flash. So if you can avoid writing identical data to the flash, then do so. Okay, so we check first, and then if our data does not match what is currently in the flash, we say should write is equals to true now, and we break out of the loop and we continue. Because as soon as you hit a not equals condition, then there's no point in continue doing the reads and whatever. You just continue on. Okay, let's just build that. Okay, 6 warnings, and it's most likely unused. And we say in our write function, we say if, and we say our validate function, we say not validate. So if we don't need to, let me just double check this logic. If this is false, we should write our data. Okay, yeah, that's correct. Let me just see here. Okay, so we take in our page start, our parameter flash data, and then our data len that we've calculated out here, and then we just return whole okay over here, because the data that we want to write to the flash is identical to the data that is currently in the flash. Now we need to calculate the number of pages that we are going to require for our write. So we take again our callen function. We say number of pages callen, and that is going to take in the length of our data, so len, but we need to do a different divisor, and this is going to be a macro flash for page underscore size. So where did I find this macro? We go to open declaration, and then you can see in our flash hole ex, which is, let me see where that location is. That's going to be in our drivers, our whole flash drivers. We can go in the include section, and then the flash extended. I assume that's what the ex4 stands for. Anyways, let me just find that macro again. Okay, you can see here for all these STMs, the flash size is 400 hex. Now 400 hex translates back to 1 kilobyte. Okay, so this is going to calculate the number of pages that we require. Next parameter is going to be const another uint32, and we're going to say page underscore size underscore u32 equals to the page size divided by the size of a uint32. Then we're going to create another uint32, and we say that is the page underscore offset, and that's going to be equals to our page start. Now this is going to be our counter depending on the number of pages that we are going to run. This is going to offset the page. For our first page that we write, we start with the start, and then we sequentially go down the page number by incrementing this address by 1 kilobyte. Okay, then we create another uint32 again, and we say this is the page underscore buffer, and that's going to be the size of our page size of a uint32. So we create a buffer of the size of a single page, and we're going to set that to uint32 max, and to be safe we say mem set page buffer uint32 max, and then we say size of page buffer. So uint32 max, there's the value. It's literally just a string of ones. The default value in an STM32 for a page is all ones. You'll see in some cases, you'll see on other ARM processors, I believe it's A5, there's some logic behind that will reduce the wear on your flash if you write an A5 to it. Then we include a flash erase init type def. Wonderful naming. So this is also included in the whole flash. Here is the definition of it. It's a flash erase structure definition. So this is the type of the erase we are going to do. This is in which bank we're going to do it, and the page erase address. So this is going to be usually be the start of your page. So let's see here. Initial flash page address to erase when mass erasing is disabled. This parameter must be a number between min, okay, so the start of your flash, and the max is the end of your flash. So actually no, the end of your bank. So if you have more than one bank, it's going to be this, okay, and this is the number of pages to be erased. So the number of pages, very straightforward. We have calculated all of these beforehand. Okay, so now we need to populate this, which I'm just going to copy over. Okay, flash erase, we are going to do a flash type erase pages. So we're going to do page erases and not a mass erase. So we're only doing one page erase and not a mass erase. Okay, the number of pages is always going to be 1 because we're only erasing one page. Now the flash bank is defined here. You can see for other STM32s, if it has two banks, you got bank 1 and 2, and both banks. For our case, we only have one bank to erase, and then our page address is going to be our page offset, so over here. Okay, now next we need to unlock the flash to allow it to erase the flash. So we're going to say our ret value, so this value that is our whole status def, is going to be whole flash underscore you see that, unlock. Okay, and that's going to be equals to that. Okay, then we can have a look at this function. Okay, you can look at these functions directly. So effectively all this does is it unlocks the flash and makes it available for writes to the flash. So a write operation is anything like erase or obviously writing data to it. It just says unlock the flash control register. It just enables writes to the flash. Very simple. Okay, then we say if our ret, so our return value is not equals whole underscore, okay, then we return our ret, and this is not equals, and we copy over another function which is whole lock. So this disables writes to the flash. You can see here, lock the flash control register access. Very simple. Disables any erase or write operation to the flash. Okay, so this is our failsafe, and we return. Now that the flash is unlocked, we are going to say for I equals 0, I is less than the number of pages, and we say plus I. Okay, so we have a loop for writing data to the flash memory, and we say you can actually move this to here. Okay, and we say another for loop, or we say j is equals to 0, j less than our page size, and then we say plus j. All right, and then we take our page buffer, we say j on our page buffer, and then we say read. We're going to commonly use this read page ADDR. Okay, so what we are doing here is, because we need to write to the entire page, we first need to pull all the data out of a page, so read all of the data, and then we need to do the changes for the new data. So first you read your entire page, change what you want, erase the page, and then write your new data to the page. Okay, so this is what we're doing here. We're pulling out whatever data is currently in the page, and we're going to say if I forgot a variable, this is going to be another uint32, and that's going to be the page underscore rem, so the page reminder, and that's going to be our data length. Okay, so this is a variable we're going to use to keep track of how many bytes we still need to write to the flash. And we say if pachrem is divisible by the page size is equivalent to 0, and we need to put that into brackets for readability's sake. And then we say if pachrem equals to 0, then we just break out of the loop simply because we have written all the data to the page buffer that we need to. Then we do another for, just grab this entire for loop, and that's going to be pachrem and our j value, and that's the for loop. Now we're going to do a else. And instead of pachrem, we are going to use the page size here. This case handles the, let's say your data does not quite fit into a 32-bit block, then this handles your trailing data, okay? Your remaining data that does not exactly divide. Otherwise, we do this normal for loop for the entire size of what a page would be. All right, okay. Then we declare a uint32 underscore t. Again, what's this? Okay. uint32 underscore t, and this is going to be erase error, and that's going to be equals to uint32 max. All right, so all f, and we're going to take our page erase address equals page offset, and then we're going to say ret is equals to whole slash ex underscore erase in lowercase because we can't stay consistent in our SDK. We're going to take our p erase in it and reference it, and then we're going to do our error erase over here. Okay, so let's look at this function. So this is perform erase or erase on the specific memory page. To correctly run this function, you can see here the whole flash unlock function must be called beforehand, and the lock to disable the flash memory access. Recommended to protect the flash memory against possible unwanted operations. Okay, fairly simple. P erase, that's our structure. Now it just contains the information. Then P error, page error pointer to a variable that contains the configuration information on faulty page. In case of error, -1, this is -1, means that all pages have been correctly erased. So we want, this is the most odd thing ever that you are returning a -1. They probably have a reason in the datasheet for it. I don't care. We are returning -1. Okay. All right. Then we say if page erase error is not equals to a uint32 max, then we need to lock the flash again. And we are going to return whole underscore error for that one. And what does ret return? Whole status. Okay. Let's look at the function itself. So I assume it's returning whole okay. So we just duplicate this function and we replace page erase with ret. And this should be whole okay. Okay, so if ret is not whole okay, we lock the flash again, we return whole error. Basically the same check as here, but don't know what the difference is. But oh wow, don't know why you're returning two errors. Now we do another for loop. Okay, we say page. There's a slight bug here. Should be J. Let's just double check all of this. And that should be J as well. Alright, going to be J. Okay, so now we're actually finally going to be writing data into the flash. We're going to say the ret value equals whole underscore flash, and then we're going to say program. We're going to get this macro, just copy it, and this is going to be a flash type, let's see, program, and it's going to be a word program. All right, let's have a look at what that does. So you got three types. You can program a half word, which is 16 bits at a specified address. You can program a word of 32 bits and 64 bits. For all intensive purposes, we are going to use the 32-bit style because everything has been set up to calculate a 32-bit buffer, and it also divides nicely into a kilobyte. We say if ret not equals, I forgot something. This is going to be the page offset plus j times the size of the uint32, and that's going to be our page buffer. All right, okay. Now let's look at the flash program. The programs a half word. If a erase and a program operation are requested simultaneously, the erase operation is performed before the program one. Okay, great. Flash should be previously erased before new programming only. Exception to this is when this address is programmed. I can't remember why you would do this. So we tell it the type, we give it the address, and we give it the data, and it returns a whole status. Okay, then you can see here in the notes that the flash should be erased before new programmation. Then we do our flash, and if our ret is not whole okay, then we say our error is equal to whole underscore flash get error. Thank you, IntelliSense. Okay, let's see what whole flash get error is. Get the specific flash error flag. Flash error code that returns. I can't remember what these error codes are or whether defined. Ah, here they are. Okay, so here's your flash error codes. If you have a programming error, a write error, an option validity error, that's what's going to be returned. And then we need to again lock the flash, and we are going to return error. All right. Okay, now we are at the end of the loop, so the per page loop. What we do here is we take our pagrem minus equals our page size. As you see, this is an int32. Possible that you can overflow. I doubt it will ever happen. Then we take our page offset and we add our flash page size to that. So now if your data goes into a second page, automatically deduct the current page that you have written and then change your page offset by the flash page size. All right, so this will loop until you have written all the pages to the flash. Then once we are done writing to the flash, we lock the flash. Then we go and grab our validate, and if our validate returns true, we return whole error, otherwise we return whole okay. So that is our flash write function with some rudimentary where leveling. Okay, let's see, what is the error? Warning, left operand comma operation has no effect. Are my braces alright? This comma, this entire, ooh la la. Okay, so that one's correct. Okay, we build, and instantly no warnings. Okay, so now we can go back to our main.cpp. So we already have this read function, so we can do this as a b0. Before we do a read, just to clear out the flash data, and we can say, like this function flash, and we say write. Okay, we take this function, we swap it out for a mem set, and I'm going to just pick an arbitrary value, so 0xA5. Now we can place our debug here, we can build, okay, place another debug point here. Actually, let's move it to here, and we can start debugging. We can see our memory browser, you can see it's all ones. We step forward, and if we step over, okay, retry that. We resume. So I'm going to step into, I want a breakpoint at the whole one, breakpoint the one over here. Okay, step over, okay, I'll unlock. All right, let's see, number of pages is 0, can't be. Just restart this, play. What has been done incorrectly with calculate length? Programming calculate, so that should at least give us 1. Okay, and we say step into here, data len, random value, div, that's 240. Okay, we step over, that's 0, and then it doesn't trigger the div. Okay, let's just see what this evaluates to. Expressions, can actually remove these, add new expression, it's dividing by 0. Small correction, we say if data len, we say this turn, that should solve our problem. Okay, we reprogram. Okay, well, let's look at the memory. There we go. You can see here, you can calculate this out, but the entire flash is 5A55. Now we can see our breakpoints, variables, flash data is going to be all zeros in it. So if I do a step over, and we just click on that one, you can actually see that it's the same yen value. I think that's yen. Where's the hexadecimal value that you can see? It's A5. So if we do 1024, which is 1 kilobyte, this is one page size. Let's say plus 30, and we change the value to 33. Doesn't really matter what. And we restart our debug session. We can say, then we resume again. We do the flash write. You can see the entire, is this the entire page? Looks to be the entire page. Let me just see where the next offset is. So the next page offset is FC00. Okay, let's just do memories here. We take this 0x. Okay, there we go. You can see here in the memories view, this is where our page starts. We did 30 bytes over a page size, so this is 4, 8, 16, 32. If I make this 32, it should fill in those last two memory addresses over here. So let's quickly do that. Okay, X. Okay. You can see there's A5. This should become 33 now. Resume again. Math is failing me. Let's do 1 byte just for kicks. We make that 66, 6x. We save this because I'm looking at the wrong address. Let's look at the start. So that's 66. We do 2 and we make that 88. Just restart this program before it. Want to render as hex. To render this as well as hex. Okay. This is going to be 88. Step over. So that wrote 2 bytes. So wait a minute. Something is reading wrong here. 1024. Okay. Let's make this IDE. So this is going to be exactly 1 page right. Okay, you can see here exactly 1 page right. 2 plus 1. Make it. Now we'll keep it IDE. So only 1 byte in this register should change. We rerun this. Render as hex and render as hex. Okay, render as hex. We do +2 there. Step over. Okay, so it's something wrong with the page size calculation. Okay, so this should give me 2 pages. Okay, so now we step into, step over, step over, step over, step over. Okay, that should just give me a calculated length. What just happened? What an annoyance. Okay, so my flash is reading identical. So let's just make the DD and we restart the debugging. So that was the wear leveling that just kicked in. Okay, step into, step over, step over, step over. Data len. Okay, that's 256. Okay, is divisible by 4, so that's fine. Step over. Okay, step into. This should give me 2 now. So len div should give me 1. You should see the expressions. Okay, so it does give 2. Okay, number of pages. We check the variables. Number of pages is 2. That's correct. A single page. Okay, so this should run twice, and it did not. Okay, now we need to change the flash data again. Make it CC. Restart. We just debug. Some more debug. Okay. Page rem or page rem. Okay, where's this one? Okay, 256 minus page size. Page size UN32. So this becomes 0, which is not possible. Okay, I'll pick this up at a later stage and fix it. Okay, so not even 5 minutes later, I have found the issue. I Control Z. You can see here that I was taking the modulus of data len. Since I already do the division here, data len will always be 0. So this should be len. So if we go to our main, we change this to 1. We start debugging again. Let's place our breakpoints beforehand. And we can see here. And then we can do a resume and look at the flash memory here. So you can see 3, and then if we resume, just take out that breakpoint, this breakpoint, you can see 111 is written in here to the following page. So this FC is the next page to be written. If we resume again, just pause it, you can look at our variables, flash data close to the end. We can see all our data is at 17, and that is 11 hex. If I say 32, offset there, and we say, and we actually try to write this in so we can check the validation now. Okay, we say resume, check our hexadecimal, we do a flash write, and then you can see here the final blocks are also written with 1. Okay, so that's how to read and write to the flash of an STM32. A like, share, comment, and subscribe is always appreciated. Thank you. Have a nice day.